Good afternoon, everyone. If you remember last time we were talking about the effect of pH on the potentials, on the reactions that occur in the environment, and I showed you and gave a handout with a potential pH diagram on it. This is a very slightly different version of the one you got on the handout, and it's very slightly different because it labels. Let me just check. Yeah, the one on the handout actually indicates phases. This one says what's happening. So you get corrosion at more anodic potentials. At cathodic potentials you get immunity, just left with the steel or iron unreacted. At high pH you can get some corrosion. At low pH you get a lot of corrosion. In the middle of the pH range you can get passivity, that is to say the material will start to oxidize and then stop because the surface layer formation prevents further attack. So those are the three areas that you get in all potential pH diagrams. The immunity, corrosion and the passivity. And they move around a bit depending on what type of alloy you've got, but they all are the same. So if I show you another one, this is a map for chromium. You don't need the details at all, but the same principles apply. At low potentials, at cathodic potentials, you've got immunity and no reaction. At high potentials on the acid side, and also in this case in the more extended region on the alkaline side, you get corrosion. And then there's an area in the middle where some stable oxide forms where you don't get corrosion. So the principles are the same even if the shape of the plot is different. And these can be calculated out from thermodynamic data for different temperatures, for different concentrations of solution. And it gives you a general idea of what might happen in your environment. It doesn't say anything about how fast that will happen. And that's really where the kinetics of the corrosion process come in. That's really the bit that you're interested in. How long will it take before it corrodes away? So it just says whether it will or whether it won't corrode. On this diagram, there are two dotted lines A and B, just as there are a couple of lines on your diagram on your handout. So I'll put the one up in the handout, that's probably the best thing to do. Okay, so this is the one you had on the handout. And these two lines, first of all, their slope is 59 millivolts per pH unit, which is the slope from the Nernst equation. So that's why they're sloped instead of horizontal. But they're actually for the cathode processes. So if you've got an anode process, you've got an equal and opposite cathode process. And in this case, there are two possibilities. And we'll look at the reactions in a little bit more detail in a minute. But the top line is the line for oxygen reduction. And the bottom line is the line for hydrogen reduction. So they've added the lines for the cathode process as well as the anode process on the diagrams. Actually, it might be on the other side. Yes, it is. This is also on your handout, this is on the other side. So there are those lines. A hydrogen line for hydrogen reduction. And that you can see almost goes through 0 millivolts. Remember the hydrogen electrode was the standard and they decided that would be value 0. So that makes sense. In 1 molar acid solution, do you remember it was an acid electrolyte? So if you go into 1 molar acid, the pH is down here somewhere and the intercept is at 0. So that's the hydrogen line. Your oxygen line is much higher up, but runs parallel with the hydrogen line with this 59 millivolt per pH unit slope. When you look at the way these diagrams are constructed, they're based on looking at individual reactions. So the number relates to a particular reaction that's going on in the system. And some of the lines are horizontal, and they're horizontal because so reaction 1 is iron being oxidized to iron 2+. That should be 2+, not 2- for some reason. This reaction doesn't involve hydrogen, doesn't involve pH. It's just metal going to metal ions. If you take another reaction like 3, it's iron hydroxide plus hydrogen ions producing different oxidation state of iron and water. So it involves hydrogen ions. Yeah? And therefore, it has some response with pH. So the lines that are sloped means the reaction involves hydrogen. It involves pH. The lines that are horizontal don't involve hydrogen ions. Yeah? So that's all it's... and each line relates to a particular reaction that's being considered thermodynamically. I should say, I don't know whether I've got it... So, there's your corrosion, there's more corrosion over here, here's your immunity, there's your passivity, and really the two diagrams on either side of the page are identical. So I've just added, this is what you can see on the other diagram, a little bit of corrosion here, a bit of corrosion there, immunity here, passivity in here. And then there's one other thing to note, and that turns up on here. So, actually there's a key on the bottom, I'll see what I can get that in. Let's try focusing now and see what's in the habit. So, there are two possible cathodic reactions, this oxygen reduction, which we'll look at in a minute, and the hydrogen reduction. The reason why their reduction lines are put on the chart are to indicate when they might occur. So, if you're in this region here, you can get corrosion of the iron, and you can get oxygen reduction. So that's what this dashed line, striped line means. So, in other words, as long as the potential is above the hydrogen line but below the oxygen line, then you can get oxygen reduction. If you are below the hydrogen line as well, then it's possible to have hydrogen reduction or oxygen reduction, or both occurring. Yeah. So, below the line, you can get the reaction occurring. You still get the corrosion, you still get the anode process. The corrosion will occur right down to this horizontal line here, but the cathode process is either oxygen reduction between the below the oxygen line, or oxygen reduction or hydrogen reduction below the hydrogen line. Does that sort of make sense? Yeah. And similarly at the other end, if you're above the hydrogen line, you can't get hydrogen reduction, you can only get oxygen reduction. Below the line, you can get either. So we can, by going to the atlas of potential pH diagrams, get an idea as to whether our material is going to corrode or not. But we don't know how fast. What we'll do next is I'll just say something about the anode and cathode reactions. So we've got the oxygen reduction and the cathode, or hydrogen reduction sorted out in our minds. So let's just go like this. So some people don't like chemical equations, that's fine. So metal produces metal cation plus electrons, and that could be Fe going to Fe2 plus, or it could be aluminium going to Al3 plus, and so on. And there's a double-headed arrow there, which just says this is an equilibrium. The process is reversible. Yeah. Remember, we're in a state of dynamic equilibrium at in the process. That Al3 plus, or the Fe2 plus, or the whatever the chromium 3 plus, whatever the corrosion product, then reacts with the water, with the solution, to form eventually to form oxides. There's the cation, reacts with water, produces an oxide, plus some acid. And you remember we said that you get local acidity round the anode. So we may have multiple little anodes and cathodes around the surface of the material, depending on reactivity of the surface in contact with the solution. But the electrons that are generated in the first process are going to go around and be consumed at the cathode in one of the two possible reduction processes, the oxygen or the hydrogen. And they look like this. So one possibility is the oxygen reacts with water to produce hydroxide ions. The other possibility is that water actually breaks down to produce hydrogen and hydroxide ions. It's much easier for this reaction to occur than for this reaction to occur. Water's quite a stable molecule. You have to put quite a lot of energy into it to break it down to produce hydrogen and hydroxide ions. So the most common most common cathodic process is the oxygen reduction process. However, at large potentials, or when you've eliminated the oxygen from the environment, then you can get hydrogen reduction as the alternative process. Okay. This is just a note about conservation of energy, which we mentioned briefly the other day. The processes have to occur at equal and opposite rates, so if you generate some electrons somewhere, they've got to be used up elsewhere. Locally, providing there isn't solution refreshment, then locally the anode environment becomes acidic and the cathode environment alkaline. And then lastly, there's just a note to sort of remind you that the corrosion processes are spontaneous because the entropy is increasing, but you can put energy into the system and drive the process in the reverse direction, which is what you do with cathodic protection systems. Okay, so we commonly get oxygen reduction, we occasionally get hydrogen reduction. That process balances the other one. We'll come back and look a little bit more at some of the theory about the corrosion process later on. What I want to do now is start looking at types of corrosion to consider how we classify corrosion, not from what environment it's in, but what type of failure we get. And so what's come around on the handout is one typical breakdown of corrosion mechanisms. So by far the commonest corrosion, of course, is our uniform attack, the general surface corrosion, where we've got random anode and cathodes occurring, and we can look at what they call corrosion rate in loss of through-section thickness in millimetres per year, or if you're an American, in milli-inches per year. and you have to be pretty careful about that because there's a factor of 25 there, 25.4. So they quite often call it MPY, milliinches per year, and we've got millimeters per year. And this is a factor of 25 between that. So 25.4. So you've got to be a little bit careful. That's fine. We can model general corrosion. Where it gets tricky is when we start looking at localized corrosion. And we're going to go through some of the common mechanisms for localized corrosion. I'm going to show you some samples and talk about what happens. So looking at the through section thickness of your structure, your pipe wall thickness in your case, and measuring how that changes with time, monitoring it, you can get a general corrosion rate for that material in that environment and work with that both for plant life extension and also for insurance purposes. It all goes wrong once you start getting localized corrosion because the anode is locally focused in one area. The structure appears to be in quite good condition, except for that one area where you get the failure, whatever it is. And the example there is just a pitting attack, which I'll show you some more about later on. This is some data you don't need the details of, but it's just some data for corrosion failures in the chemical and offshore industries, and the general corrosion failures in each case is about 15% of the total failures. Stress corrosion cracking, which is a localized effect, which we'll talk about later on. Pitting corrosion and intergranular corrosion, these are all local effects, actually represent more of the failures than the general uniform corrosion failures in the chemical industry. So there's a lot of localized corrosion out there, and it's actually your worst enemy. Okay. So on your handout you've got some of the common forms of localized corrosion. We're going to go through some of them. There's the uniform attack, just getting a general loss of the through section thickness of your structure. The next thing we're going to talk about is galvanic corrosion, and the reason for that is that where the interface is between the anode and cathode material, you get enhanced removal of the anode material. And that's related to the concentration of current flow. So there's more current flowing close to the interface than there is further away from the interface. It's called current throw, and it applies to all electrochemical cells. The current takes the majority of the current takes the shortest route. Yeah. It doesn't want to have to wander all the way along the surface out here. It goes straight round. If it can. Actually, the electrons are flowing that way, aren't they? From the anode to cathode. Conventional current is flowing the other way. Okay, so we'll say something about galvanic corrosion next. Just do that. So you've had this image before, just suggesting that there's two half cells, in this case for iron and zinc, and but the same is true for any couple of dissimilar alloys or metals. And so you need to use the galvanic series, which we've talked about already, or you need to insulate them from each other. So you've had the cell before, that's on the handout, okay, from last 2 weeks ago. This note under the bottom is just to say that galvanic corrosion can be bad if you haven't planned, but you can actually use it to protect a structure by what they call sacrificial anode, and I'll show you another example of that in a minute. It can also be used as a way of generating electric power. So sometimes you can use it for a positive purpose. Okay. Oh, colours are terrible. Why is that? White balance. That's still not behaving itself really. Okay, let's try it with the other line. I've never seen that image so bad. That's slightly better. Oh, right. Do you recognise the flag? Yeah. Yeah, we're in Portugal. Right. This is. I'm very sad when I go on holidays. I take photographs of corrosion. This is Cape St Vincent. This is the most, reputedly the most westerly point on the coast of Portugal. So Portugal sort of has a corner on it between the Atlantic and the Med. Yeah. So it's right on the corner. A nice, beautiful part of the world, but it has a sea on both sides of it. So that means you have potentially quite a lot of atmospheric salt in the environment. Don't think these are showing up very well for some reason. This is the bottom of the flagpole at the fort at Cape St Vincent, and it's a classic galvanic corrosion situation. What they've got is a steel bracket with a stainless steel bolt through it. And you can see on the back wall a load of corrosion product being slowly washing off the bracket, because the bracket is corroding away. And that sort of thing is quite typical in a load of situations. And I've got another one which is a bit nearer to home. Try out that one. This image is actually showing part of the baffle plate in the Emerson cavitation tunnel, which is getting moved to Blythe from the Armstrong building at the moment. So this is part of your own marine technology school, and it's a big flow tank basically. And they did an upgrade. What they're interested in is parallel flow through the chamber. So they've got, in order to get that parallel laminar flow, they put a baffle plate in, which is a honeycomb plate on the right hand side there. And so the solution is flowing through that plate. This piece of equipment's been around for quite a long time, and it was decided to do an upgrade. They decided the baffle plates had been getting a bit of wear, and they would replace them with a brand new stainless steel baffle plate, which is what they've done. This is a stainless steel honeycomb for the solution to flow through. Trouble is, the rest of the structure is cast steel, and before long they began to notice that the solution in the tank was getting cloudy. So on the telephone they get, and of course it's just galvanic corrosion. The solution, not sure whether you get, these images aren't as good as they should be. Let's take that down, maybe it'll show up better. So there's your baffle plate, solution's flowing through, and what they've done, I don't know whether you can see, maybe here there's a little bit of gasket showing, a little bit more there. What we've had to do is put a gasket in between the baffle and the cast steel case, and also put washers underneath the bolts, so there's a gasket material, and that isolates the anode and cathode. So even in organisations that should know a lot better, things go wrong. And I mean, it was a professional marine engineering organisation from Germany that came in to do the upgrade and the overhaul of the equipment, and they thought, yeah, we'll put a stainless steel baffle in, it'll be great, you know. Yeah. Months later we got it fixed. Okay, so galvanic corrosion can be an issue. Sometimes it can be good news, so we can use it for coating materials. And so zinc coating of handrails, of roof sheets. These are the corrugated roof sheets used in on factories and so on. In the automotive industry, for things like so car bodies, also in roofing sheets, also in handrails, and quite a lot of other situations, they coat materials in zinc. The two ways of doing that: you can either dip your object into a molten bath of zinc and pull it out, in which case you'll end up with a really thick layer of zinc, and the surface finish is a bit rough, because it sort of drips as you drain the excess zinc off, and it's a bit of variable thickness. The other way to do it is to electroplate it, and if you do that, you end up with a controlled thickness. You know how much zinc you put down. The surface finish is a bit nicer as well. You can control how shiny the coating is. The zinc initially just behaves like a paint coating. It is a barrier. It stops the solution contacting the steel underneath. So that's its first role. However, if you've got a piece of steel and it's got a zinc coating on top, in service it's not unlikely that zinc coating could get damaged. So we end up with a hole in the zinc coating. When that happens, the environment can now contact the substrate, the steel, and you'll start to get a sacrificial anode effect. The zinc, because it's more reactive than the steel, will act as the anode, start to corrode away. The iron underneath that's exposed at this point will be the cathode and be protected. So it's then acting as a sacrificial anode. What happens if the damage here is not too large, if it's something like a scratch, is that the damage chokes back up again. I think I said a while back the volume of the corrosion product is greater than the volume of the parent metal it was created from. Did I say that? If I didn't, it's important. So once you start to build up zinc oxide or zinc chloride, it begins to grow and it can fill the hole again, if it's a small hole, if it's a scratch. So that's what I mean by oxide choke. So it has a possibility to repassivate, it's like a self-healing coating. Yeah. The other thing that's interesting about zinc, at least from the marine point of view, is that the corrosion products are often white in colour. Unlike iron, where you get brown and black and green corrosion products, zinc produces white compounds. And that's very good for the shipping industry, because the bulk of the hulls are white. So you want the corrosion product to be white, and then it doesn't show up on the hull. So quite a lot of the paints that are used for shipping contain zinc as an additive. Some of them also have aluminium in it as an alternative, but zinc is quite often used. And it gives you this barrier sacrificial anode oxide choke sort of operation, which is very useful. This image here is the leg of an offshore oil platform, and this is sacrificial anodes, in this case large blocks of aluminium. So that is a big block of aluminium bolted onto the leg of the platform that's going to be submerged in water, and another one, and another one. And they calculate out the size of the block and the distance apart they should be, to ensure that the steel, the tube, is always at a suitable cathodic potential. So in a sense it's sacrificial anode, but scrapping the barrier stage, you're going straight to, right, the anode and cathode are exposed to the marine environment in this case.
Why would they use aluminium rather than zinc on a steel structure? Because I mean, I'd start looking at blowing the curtains off the steel, wouldn't
You start?
If there's too much potential difference, you start blowing the curtains off the steel.
Yeah, if there are a number of factors. Aluminium alloys, magnesium alloys, and zinc alloys are used quite commonly. A lot depends on how your structure is coated, to what extent it's coated, you know, and you're right. If you overprotect, then you've got a problem that you might start generating gases and delaminating a coating. If you've got coating, and what its permeability is, and so on. There are a lot of variables, but they are commonly used. One of the other, not that we should really get into it now, but what you get is, if we put a pipe in the leg of this platform, and you put a block on it and bolt it on, it's electrically connected, yeah, and then there's another one here, electrically connected. What you get is a high cathodic potential here, a high cathodic potential here, and in between, not so good. So if you plotted potential against the distance, it's pretty cathodic near the sacrificial anode, then it starts to drift up and then it goes back down again. So you're getting this, you don't get a uniform potential across the distance. It's because of this throwing power of the electrode, this current fall off.
Line of sight.
Sorry?
The line of sight, the electron. Is that one?
It's to do with the electrons will take the shortest route. That's assuming that you haven't actually got any coating on there. If you've got a coating on there, then these, and it's of good quality, then these aren't doing anything until you get a hole in the coating.
Okay.
Yeah, and then you've got a question of how far is the current flowing, what's the cell resistance, because this cell, just like the corrosion cell, is obeying Ohm's law. So the question is how big R is. Yeah. You've got another question with these anodes, and that is, what's your accessibility? Are you going to be able to go down and replace them? Maybe you can't. In which case, it's better to put a few more on than have too few. And so there are a number of other factors that come into play. This is the same thing on a steel hull of a ship. So this is the hull of a ship, and they bolt, in this case it's a zinc alloy block, directly onto the hull of the ship, and that will give excellent cathodic protection to the steel plate. So there'll be a block every so often. So it's the same thing. So we're harnessing localized galvanic corrosion in a positive way to protect the structure that we want. Okay. Don't need the details of that at all, but I'll just put it up just so you can just this is I don't know why the colour's gone on this. It's not very good. This is just what's that? Triangle base. Come on. Close. That's close enough. This is just saying, okay, you can use it for electrical power. The old-fashioned voltaic pile was just alternate discs of copper and zinc with a saline solution in between them. After that came a variety of torch batteries, which basically involved corroding. Oops, it's gone again. Come back, come back, come back. And stay. No, stay. A variety of torch batteries, which basically involved corrosion of zinc again. So zinc carbon, zinc alkaline batteries, your Duracell battery, it's just corrosion of zinc produces the electricity. And then more recently there's been a variety of emergency supply cells, particularly for shipping, and they're based on corrosion of aluminium. So the cell is just dry until they need the power, then they throw it over the side and fill it full of seawater, and the seawater just starts corroding the aluminium, generating power for the emergency lighting and so on. So yes, galvanic corrosion can be bad because it gives localized attack of a material, but it can also be useful. Okay, I think we'll stop there. We'll talk about pitting corrosion and crevice corrosion and some other localized corrosions next time. Thank you.
Thank you.
Try and get that fixed.
Belki bizim anne çıkın üstüne live önce bana verir misin? question. I asked him to do recently. If you are not comfortable with CFT. No, that is the integration derivation is just for operation. Have you found anything? Oh, my brother. Where is my big bro? Ah, he's sitting over there. Big bro will go. Big bro.
I'm fine, but anything
From 2 p.m. on, yeah.
so once you're around,
I'm just about. Oh, sorry, I'm just.
Don't worry.
I'm just about done with the crosses. I guess tonight or tomorrow or something. I'll get
I'm not
to
ready.
what I've done with crosses.
So really, tell us.
If you have a look at Ben's and Steve's do the same kind of series, if not, I'll keep on following them.
anything I've made to do is
Strong malls, I think that's really good. But then
types
basically here,
Okay.
into
They were focused.
but it meant we had two. Please just tell me you're going to the pub afterwards. Nervous about this test.
It's tempting. Let's come off the ladder.
So you're not doing it, I've already asked you.
Yeah, I'm going home. Chinese at 7. Central.
Thank you. Sorry, you're right. It's 18th, isn't it? That's okay. It's just more vocab every time.